Jā, labi. Ir, ja? Puiši, ir skaņa? Jā. Labi, labdien, good morning everyone. Tātad visiem, kuri man šobrīd dzird latviešu valodu, jums visdrīzāk labs ieteikums būtu Facebook kanālā palikt, ja jums ir ērti abās valodās konferencē sekot. Mums šodien ir nopietna darba diena, bet 2 stundās mēģināsim iespiest daudzas lietas. Man liekas, tāpēc ir svarīgi arī sev ērtā veidā to klausīties un nekautrēties, ja gadienā ērtāk ir lietot vienu vai otru vai pamīšas valodas. Ja jums ir vajadzīgs tulkojums, tad savukārt uzmeklējiet mūsu Zoom linkā, un Zoom linku tieši tagad Facebook komentāros esam nopublicējuši. Pieslēdzoties Zoomam, jums savukārt ir lieliski iespēja izmantot augstas klases profesionāļu, proti mūsu tulku un tulkotāju, tātad iespēju, tulkotāji tie, kas rakstiski tulko, tie, kas var sekot tulku pakalpojumu. Tur jūs atradīsiet arī iespēju tātad meklēt uz podziņu interpretation, kas nozīmē, ka jūs varat ar kanāliem vienā vai otrā. Tad latviski un angliski, un arī tiešām šīs lieliskās konferences daudzi lektori ir katrs savā sev ērtākā valodā sagatavojuši savas prezentācijas jautājumus, gan mēs varam uzdot abās valodās. Tā kā nekautrēties, zinu, ka latvieši ir ziemeļnieki kautrīgi, bet šeit nav īstais mirklis kautrēties, jo tieši Latvijas piemērs lielā mērā ir par pamatu šim lieliskajam starptautiskajam projektam, kurā, būsim reāli, ir jāizpēta, kas kurā vietā varbūt būtu piemērotāks gan lauksaimniecības lietām, gan varbūt arī pat citām lietām. Augsnes vērtības karte principā ir ļoti svarīga, Latvijas vērtības karte, un mēs daudz ko mācamies no tā. Arī, protams, daudz ko tā, ko jau izdarījuši ir mūsu kolēģi Nīderlandē, Somijā, un lūk, šīs pieredzes mēs arī apkoposim un mācīsimies viens no otra arī šodienas konferences gaitā. Tā kā es mūs visus apsveicu, ja ir patiesa interese, tad noteikti ir jābūt arī patiesiem, būtībā pat tautsaimniecības panākumiem ilgtermiņā, vai ne? Ja mēs zinām, kas ir augsnē, tad mēs zinām, ko vislabāk no šīs augsnes var dabūt ārā. Es domāju, ne tikai vīnkopībā, visās iespējamās nozarēs tam ir ļoti liela lieta. Šoreiz vairāk koncentrējamies uz kūdraugsnēm, gan novērtēšanu, gan modelēšanu, gan pat mašīnu mācīšanās, cik interesants aspekts, vai ne, šo lietu pētīšanā tālāk. Tā kā, man liekas, te katram gan augsnes zinātnē, gan varbūt pat digitālā zinātnē vērstam prātam būs ko dzirdēt un novērtēt. Tātad mēs strādājam šobrīd gan Facebookā Zemkopības ministrijas, kas angliski būtu jāmeklē kā Ministry of Agriculture of Latvia kontā. Ja jūs gribat ērtāk Facebookā mums sekot, jūs varat sekot arī YouTube kanālā, un jūs varat, protams, arī iepriekš izsūtītajā Zoom linkā. Vēl viena ļoti svarīga lieta, kas mums visiem kopā šodien būs jādara, būs tādā nopietnā, starp citu, ar padziļinātiem jautājumiem aptaujā jāpiedalās, un tad mums būs vajadzīgas prasmes rīkoties ar menti.com. Un menti.com, kad pienāks mirklis, mēs izziņosim jums arī kodu, un tad ievadot to kodu, mēs nonāksim vienā anketā. Lūdzu, atbildiet arī sirsnīgi, un zinot jūsu daudzu šeit iesaistīto cilvēku kompetenci, šai aptaujai nav, kā teikt, izklaidējošs raksturs. Tā ir diezgan liela jēga tajā, ko mēs ar jums kopā darām. Man liekas, galvenais izņemot to, ka varbūt ir svarīgi pateikt, ka gan par kūra metodu, organisko vielu prognozēšanu, gan par tālis pēc datu tālāk jau izmantošanu šajā kartēšanā un ko tā mums var dot. Uzlabot telpiskie dati arī būs uz mūsu, kā teikt, apspriežu galda lauksaimniecības kūdras augsnēm, piemēram, Somijā. Bet, Somija un Latvija, lai man piedod, Somija ir ļoti līdzīga šajā ziņā. Varbūt vienīgi Somijam vairāk ezeru, man liekas. Bet kūdras, ja es pareizi saprotu, mums ir 8. Baigi neatpaliekam no jums, draugi. Katrā ziņā mums būs ļoti liela interese, es domāju, pavadīt šo intensīvo dienu kopā. Un man liels prieks, ka Latvijas valstī vēlme šajā ienirt ļoti tiešām dziļi, varbūt ne tik dziļi, augsnes vērtība gan, un tur mums tādus atklāšanas vārdus vai ceļu vārdus šīs dienas galvenajiem darbiem grib dot Dats Cerāja. Viņa ir mūsu Zemkopības ministrijas valsts sekretāra vietniece.
Labrīt, cienījamie konferences dalībnieki! Esmu priecīga un gandarīta, ka šodienas augsnes izpētes projekta konferencei pieslēdzies tik plašs dalībnieku loks gan no Latvijas, gan arī citām Eiropas valstīm. Jāteic, ka Norvēģijas grantu finansētais Latvijas augsnes izpētes projekts ir ļoti plašs un skar dažādas jomas. Tas ir gan ambiciozs, mums svarīgs un ļoti nepieciešams. Šis projekts atver dažādas mērķu grupas, tostarp augsnes apstrādātājus, jeb lauksaimniekus, zinātniekus, politikas veidotājus un nevalstiskās organizācijas. Pagājušā gada konferencē lielāko uzsvaru likām tieši uz zemes apsaimniekotājiem un lauksaimnieku nevalstiskajām organizācijām. Šogad ar šīs konferences starpniecību galvenokārt vēlamies sasniegt esošos un topošos zinātniekus un politikas veidotājus. Nenoliedzami, lauksaimniecībā viens no galvenajiem ražošanas pamatresursiem ir zeme, bet klimats mainās un mēs arvien spēcīgāk jūtam šos pārmaiņas sekas. Un tieši augsnei ir nozīmīga loma šo klimata izmaiņu mazināšanā. Tā ir nenovērtējama oglekļa krātuve, bet dažādi augsnes degradācijas veidi un neilgtspējīga zemes apsaimniekošana rada augsnes oglekļa krājuma samazināšanos un oglekļa dioksīda emisijas pieaugumu atmosfērā. Tādēļ ir svarīgi to apzināties un domāt, kā mūsu zemi efektīvāk apsaimniekot, iespējami izvairoties un mazinot ietekmi uz CO2 emisijām. Vislielākā oglekļa krātuve ir tieši kūdraugsnes, kas atrodas gan aramzemēs, gan zālājos, gan mežos un mitrājos. Un jāteic, ka Latvijā šādas kūdraugsnes ir daudz. Lai mēs izstrādātu vidēji saudzējošas augsnes apsaimniekošanas risinājumus, ir nepieciešami ticami, precīzi un aktuāli dati. Latvijā dati par lauksaimniecības augsni ir, bet tie ir ļoti fragmentēti un novecojuši, jo pēdējā augsnes izpēte tika veikta vēl Padomju Savienības laikā. Tas ir līdz pagājušā gadsimta 90. gadiem. Un šis projekts dod izcilu iespēju Latvijai atjaunot un pilnveidot datus, uzlabot augsnes klasificēšanas sistēmu, saskaņot to ar pasaules klasifikatoriem un nodrošināt lauksaimniekus ar praksē lietojamu informāciju, kā arī aktualizēt Latvijas normatīvos aktus, piemēram, lauksaimniecības un lauka attīstības likumu. Svarīgi ir norādīt, ka augsnes datu iegūšana ir arī laikietilpīgs process un prasa lielus cilvēku un kapitāla resursus, jo šādu datu iegūšanas pamatā ir tieši reāls darbs uz lauka. Bet par laimi zināšanas papildinās, tehnoloģijas strauji attīstās, un tas paver iespējas nākotnē vairāk izmantot tālespētes datus, mašīnu mācīšanos un mākslīgā intelekta risinājumus. Neaizmirsīsim arī to, ka arī Eiropas Savienības kopējā lauksaimniecības politika pāredz un veicina dažādu precīzo tehnoloģiju lietošanu un digitālo datu izmantošanu saimniekošanas lēmumu pieņemšanā un politikas veidošanā. Un Latvija to arī ļoti aktīvi ievieš. Taču vienlīdz svarīgi ir gan politikas mērķi un pieejamie finanšu resursi, gan arī zināšanas par šo jauno tehnoloģiju lietošanu un datu izmantošanu. Šodienas konferencē mēs runāsim tikai par vienu nelielu projekta daļu, par kūdraugsnes izplatību un kartēšanu Latvijā, kas nenoliedzami šobrīd ir ļoti aktuāls temats Eiropā un ļoti plašs arī temats zinātnē. Latvijai ir ļoti svarīgi izveidot kūdraugšņu izplatības karti, kā arī ieviest augsnes oglekļa monitoringu tīklu, kas arī ir daļa no šī projekta mērķiem. Valstīm ir pieredze šajos jautājumos, kā notiek darbs pie līdzīgiem, tikpat nozīmīgiem projektiem, tādēļ ir svarīgi, ka notiek šāda zināšana un pieredzes apmaiņa. Pateicoties daudzajiem sadarbības partneriem Latvijā, Norvēģijā un vairākās Eiropas Savienības valstīs, šodien diskutēsim par pieredzi tālespēdes metožu lietošanā, salīdzināsim klasiskās un digitālās iespējas, vērtēsim iegūto datu ticamību un abu šo metožu līdzās pastāvēšanu. Un man tiešām prieks, ka konferencē diskusijās mums šodien pievienojušies augstsklases eksperti gan no Latvijas un Eiropas, kas dalīsies ar savu pieredzi šajos svarīgajos jautājumos. Tādēļ šodien gribēju pateikt lielu paldies visiem, kas piedalās šajā konferencē. Vienlaikus vēlos atgādināt, ka jau iegūtās pieredzes izmantošana, pētniecisko projektu sadarbība un apvienota projektu izveidošana, kā arī datu atkal izmantošana ir vienīgais pareizais ceļš, kas mums visiem ejams. Un Latvijas zinātniekiem ir ar ko dalīties, un esam spējīgi un gatavi piedalīties plašos un nozīmīgos Eiropas līmeņa projektos, ienesot tajos savu pieredzi un zināšanas. Līdz ar to vēlu visiem interesantu un jaunu zināšanu pilnu dienu. Esmu pārliecināta, ka kopā mēs varam paveikt daudz noderīgu darbu Latvijai, Eiropai un mūsu kopējai videi. Paldies!
Jā, liels paldies, Dācis, jums par ievadvārdiem. And now we switch to English. So the colleague Rainer Baritz works for this European Environmental Agency. And thank you for being here, explaining the whole concept probably of the Green Deal initiative and the need for a greater and reliable data. But can I start with a kind of provocation, just asking you, Rainer, when you will have all these data in all countries in the whole Europe, does it mean that you will actually narrow an options for a landowner to do something he wants to do with his own, let's stick to this soil question, that you will not allow him to do too much of something because this peatland is actually, and we don't need these emissions always. Sometimes we better keep it as it is, a storage place. So does it mean that there will be some liberties actually limited to landowners of this and kind of these projects that will probably run around quite enough, isn't it? You're wasting it. Es tad uzlieku Zoomu. We hear you, sorry, it was just technicalities, so you can proceed with your presentation, please. Sorry, I was interrupting you and misleading with this. Yes, please, proceed.
That give us an idea of the state of soils, and this is quite worrying. What you can see here also is just three main, very general statements about where soils are important. But the message that you can see is that it's not just measuring certain soil parameters and describing a soil condition. It's also understanding what is soil doing, what are the functions of soils, and how are they concerned. So the questions that we have about soils is not only about measuring more or less of something, it's also what it is there for. And if you have less, what is the impact? So the impact of how soil functions on ecosystem services is of crucial importance. So our questions to data are going way beyond the measuring of a state and trend of some parameters. Next slide, please. Thank you. So the EU European Union Soil Strategy 2030 was born and published in November last year. It's part of the Green Deal, as you correctly mentioned. The Green Deal is a huge initiative of the European Commission with the member states that involves the biodiversity strategy. And that strategy is a follow-up of a former strategy that has not yielded satisfactory effects or impact on our ecosystem condition. We cannot see ecosystems improving to the favorable conservation status which has been proclaimed at the initial strategy. So a new strategy has been established, which includes also an action on soil. And this action on soil has been written and described in the European Soil Strategy. And you can see here the vision that by 2050, all soil ecosystems are in a healthy condition. And that the protection and sustainable use and restoration of soil has become a standard of operation, of good practice of all land users, agriculture, forestry, all land users are involved also in urban areas. So this is proclaimed with the knowledge that healthy soils contribute key solutions to many challenges. Ecosystem health largely depends on the condition of soils. Next slide, please. This is a bit more in depth what this EU soil strategy suggests. There are medium-term objectives and long-term objectives. And you can see that the strategy here also connects to various Green Deal initiatives, such as the Farm to Fork strategy, which aims to reduce nutrient losses by 50% and the risk from chemical pesticides by 50%. So it's quite a list of different topics, and some of the topics or objectives also touch organic soils or peatland soils. For example, the objective that the greenhouse gas removal that is needed to reach the 2050, 2030 and 50 objectives of our climate program also involve actions on peatland. So this strategy really involves all soils and all land users. Next slide, please. This is an interpretation that I prepared for what the strategy describes in the direction of building a healthy soil law. The strategy that I just mentioned suggests that the action that could follow could consist out of a regulation, for example, that promotes and supports the establishment of healthy soils by 2050. How can this be done? Monitoring, as you can see here, will play an important role. It's a pillar of knowledge to tell everybody involved where action is needed. And this question of where action is needed, that is still not really decided of how it's done. It's connected to the definition of what healthy soils really are. So that is on an ongoing debate. It seems a simple topic, but it's not so topic. It's not so easy. Is it if the trend of parameters is declining, it's getting towards the worse? To which extent do we know how much or which soil functions are lost? How does that impact ecosystem services, do we strive for reference values or thresholds? So this gives us an idea, okay, here is an unacceptable condition, land use change must follow, which is then regulated somewhere else. We don't know yet, but it could be an option. And then the next step that is in the middle of the graph, you see then that member states will have to identify or will be asked to identify the extent of unhealthy soils and then to prepare measurement plans of what to do in this area. And then on this basis, countries can deliver and can prepare and deliver national healthy soil reports. So you can see here, monitoring is very important. How to evaluate the monitoring results and how to assess the condition of soils in the context of healthiness and what to do. That is in an ongoing discussion between the European Commission and member states representatives at the moment. Next slide, please. That is also an element of discussion, which indicators are actually needed, at least which core indicators are needed to address the ecosystem services which are of interest and which ecosystems need to provide. This is a first draft of a list of such core indicators, and of course it needs to be still discussed. Is it representative for all land uses? Do we need? How can we consider land uses or land use specific requirements to indicators? Specifications will be needed. It will also be needed to define the actual parameters we have to be measured in order to derive the indicators listed here. Then monitoring will yield information about monitoring and trend. And then there is a question of decision making. What do we take as a criterion to say this is a particular site where action is needed and that is a site where everything is okay? So it's quite a challenge. Next slide, please. I continue to walk you through a couple of aspects of policies that are related to the Green Deal. More closely related to the biodiversity strategy is a draft law on nature restoration, which probably all of you have seen. It was published in June 2022, and you can see here an indicator set that suggests a specific set of indicators for different ecosystems, and for agricultural ecosystems, drained peatlands under agricultural use are the focus. So it is suggested that member states pursue targets, re-wetting targets, relative to the area where they have drained peatland under agricultural use. That could be quite challenging, and it also requires a very specific monitoring, that is to identify which peatlands are drained, which peatlands are under agricultural use, and which restoration targets can be identified. Let's say re-wetting would be one, but there are probably also integrates of steps that you can take in order to gradually bring drained peatlands back into a restoration stage or condition which you want to achieve. Next slide, please. The climate change is also an important aspect for soils, of course. Soils play a key role in mitigating climate change. And our climate targets depend on a solid contribution by the LULUCF, by the land use change and forestry sector. And that includes, of course, organic soils. And when we look into the current reporting under UNFCCC, under the Climate Change Convention, and this is from the EU, European Union National Inventory Report 2019. And you can see here how organic soils and mineral soils in blue and organic soils in red, perform with their emissions. And organic soils, which come closest to your discussion on peatland, are a significant source of greenhouse gases, in particular, CO2 and also non-CO2 gases. Depends on which stage of degradation or active peat formation the organic soils is in. And the rough figure is that roughly 2.2% of the organic soils account for a large proportion of greenhouse gases, of agricultural greenhouse gas emissions in the EU. It's over proportional, and a focus, that's also one of the reasons why the focus in the restoration law is in fact on re-wetting, because the value of these soils is highly recognized. There are questions about what means managed and drained peatland, what is degraded peatland, how does it relate to different land uses. So the preciseness, the reliability of information is not so easy, since different inventories provide different informations. This is the official nationally reported information. When you look into European-wide data sets, soil maps, geological maps, and other informations, you may come with quite different numbers. And it will be an important incentive for improving monitoring to get more reliable figures on the effect of organic soils and peatland in terms of area, in terms of condition, and in terms also of greenhouse gases. Next slide, please. Yeah, this is a little map that we have created where we used a threshold to tell us the amount of organic matter, of organic carbon in soils, and a threshold below which important soil functions are hampered. So where we think that soils are really degraded because there is not enough carbon in the soils. This graph is excluding wetlands, but you can see as an example that it illustrates quite clearly that there is a large proportion of soils where soil organic carbon levels in agricultural soils are really, really low, to a level where we expect some drawbacks with other functions. And this is an area which needs, this is, let's say, an approach that needs to be validated regionally. And if you kind of translate that into an implementation of monitoring and a healthy soil law, for example, at some point in each country, you need to identify soils like that. This is done for Europe. You would probably want to do this at national level too, where action is needed. And for that, criteria are necessary. You can see here again that it's likely that soils like this have the highest potential for sequestration. There are various models recently developed, one of them by JRC, you can see here, which project the sequestration potentials of soils. And in fact, sequestration from the just mentioned LULUCF sector, including soils, is very important to reach the EU's climate target by 2030, which is to reduce the emissions by 55%. And the mitigation part of the land use sector is very important, and so are soils, and so are organic soils in particular. Next slide, please. Yeah, I'm finished with my presentation. Just some conclusion. Lots of work, also policy work, is in progress. There are various discussion levels with member states, with experts in the countries about definitions, about indicator systems, about monitoring. You can certainly expect that national monitoring systems must be representative across all land users. They probably need to be strengthened to be able to provide information about the effect of soil change, soil condition change on soil functions and ecosystem services. A core set of physical, chemical, and biological parameters need to be covered, as well as non-soil parameters. Soil information can only be interpreted if climatic information, also information about agriculture and forest practices is available. And I come to to the second bullet point as last. For organic soils, as mentioned before, many unknowns remain. The level of degradation, the land use effects, are there thresholds possible? So there are many questions for a project that you are conducting at the moment, and I would like to thank you with these conclusions for allowing me to present to you and to listen also to the next presentations, and wish you a successful meeting. Thank you very much.
Yeah, thank you. And of course, Rainer, you are more than welcome actually to involve yourself. Also, later on, we will have a bigger discussion. Actually, it started. Can I ask you a quick question from the Zoom chat? There is a colleague who is asking, so what is this healthy soil concept? I understand one cannot measure it with just one healthy aspect. It could be different explanation in, I don't know, you showed us the map of Iberian Peninsula. The healthy soil there would be a kind of different substance than here in north of Europe.
Yeah, that is actually what makes this so complicated. Yeah. When we are discussing right now an indicator system, of course, that needs to address all soil function, but that goes through many processes that soils are involved. And that is regionally different, that it's different in mountains and different in the boreal zone, different organic soils and different in the Mediterranean zone. So there are all these conditions. So erosion, compaction, soil organic matter decline, salinization, soil biodiversity losses. These are all different soil threats that we can observe are happening, and we are seeking for a definition of healthy soils that addresses all, but not through a single number or index that is probably hardly feasible when you consider the complexity, the regional complexity also of soils, and also the local complexity of soils when you look at soil processes. So very likely it is the predominant local and regional factors that determine the orientation of measures that eventually you take in a region to improve healthy soils. So you will not have salinization in all areas of Europe. No? So it will not be an indicator that is relevant unless you introduce salinity through irrigation. No? So we have to address in the system these conditions indeed, and it's not solved. I can say that. It's in discussion.
Yeah, well, actually, we are proud of being part of this discussion and this project, isn't it? So it's great to have this beautiful, different Europe that is so different that it never has one simple answer. It has a complex of answers. And actually, for exactly this matter, probably there was an initiative, at least from the side of Bas Kempen, the next speaker. He is a very special person because he is working for actually the International Soil Reference Information and Information Center. So there is a special digital mapping system, or at least a reliable data, which are probably still, but there are some examples. Examples from Netherlands and from Finland. So one can somehow measure at least differences, which comes up here. So please, Bas, how it works and how much of trust we can put in these new data you are sustaining, developing, and upgrading probably constantly every day.
Thank you very much for this kind introduction, and also thank you very much for inviting me for this conference. Can you or someone put up my slides?
Your slides, yes. So
yeah.
Here they come.
Get started.
This is your slide.
Time is short. Yeah, there it is. Thank you very much. I think you can all hear me well.
Yes, we do.
Okay, great. Yeah, so I was asked to. Sorry, can you go back to the
one more
previous slide? Yeah, thanks. I was asked to present a little bit about some of the work that we have been doing in the past in the Netherlands. And then I thought recently I've been working also in Finland, and I have to admit that was not on mapping peat distribution, but it was on mapping acid sulfate soils. But from a methodologically perspective, we're talking about mapping methodologies here. that is not so different. You can use the same methods for mapping peat soil distribution as for mapping acid sulfate soils. So that's, I thought, okay, that is still, it's not about peat soils, but from a methodological perspective, it is still interesting to include it in this presentation. All right, can I have the next slide, please? So let's start with the Netherlands. Thank you. So this was work that I did some years ago, almost 10 years ago. I worked on this with my colleagues from Wageningen Environmental Research, which includes the Dutch Soil Survey. So in the Netherlands, we have extensive areas of peat soils, almost 600,000 hectares, as that was mapped in the past, which comprises a large extent of our land surface. And many of these soils are intensively used for agriculture. So they are deeply drained, farmers plow them, and of course deep drainage in combination with heavy use resulted into degradation of these soils. Rainer was just mentioning that in the previous talk. So some assessments that the Soil Survey Institute did around the year 2000 show that extensive areas were degraded. Peat became oxidized and went up in the air as CO2 mainly. So then around 2008, the initiative was started to update our national soil map for the peatlands, not covering the entire peat area, because we also have some really wet areas where things did not change much, but we focused on, say, the more intensively used areas, which covered about 365,000 hectares. And what was nice about this study was that it was a combination of traditional soil surveys, so people going out in the field with maps and with their augers, etc. And we tried to combine that also with digital soil mapping that was really emerging at that time. Machine learning, I think we will also talk about machine learning later on in this conference, was still a little bit at its infancy at that time. So for this study, we did not use machine learning methods. We still relied on the geostatistical methods that were popular at that time. And the results are published in a paper in Geoderma. I put a link here, or at least the screenshot of the paper here. So you can always look it up if you're interested in what we exactly did. It was a methodologically quite complex study, so I'm really trying to give, only because I have 10 minutes, I'm only going to give a flavor here to give some idea what we did, and more details can be found in the paper, of course. Can I have the next one, please? So this study went a little bit beyond mapping the distribution of peat soils, so say presence, absence, where do we find peat soils? This went a little bit beyond that because we really want to update the soil classes, the soil classification according to the Dutch soil classification system. And we took a strategy by doing that through measuring and then modeling and mapping, say, key diagnostic properties that are used by the Dutch soil classification for classifying the different types of peat soils. And two important properties for that classification is the thickness of the peat layer and the starting depth of the peat layer. Those diagnostics really determine the major soil class that we have for the peatlands. So we had extensive field campaigns where surveyors measured the actual thickness and also the starting depth of the peat, because not all peat soils have peat starting already at the soil surface. Sometimes they start deeper in the soil. A lot of new data were collected, new observations were collected throughout the Netherlands. And what we also did in the study, we had in the Netherlands, they have a huge soil database with observations on peat soils from the past, from the 1950s, 60s, 70s, 80s, and 90s. And we try to make, it's outdated, but we still try to make use of those data in our modeling framework. So we try to combine this old legacy data with new data. And we also looked at how we do digital soil mapping, so statistical modeling and mapping of soil properties. We also looked at what are good predictive layers, GIS layers that we can use. What environmental properties are controlling the distribution but also the disappearance of peat and peat soils in the Netherlands. And among some others, we used our soil class map, our national soil map, as one of the inputs for the models, a digital elevation model with some terrain parameters derived from that. Groundwater is very important in the Netherlands for mapping and classifying peat soils, but also land cover. Peat soils in cropland areas are much more degraded than peat soils in say more natural areas, and also geohydrology we use as say environmental predictors of the presence absence of peat, and also the thickness and starting depth of the peat layer. Can I have the next one, please? I'm not going into too much detail here. Like I said, we try to use all data in our models. And of course, the thickness of the peat that was measured in the 1960s or 70s is not representative in many areas of what we find today. So we try to update these old observations. So we came up with a kind of a model to model peat disappearance based on groundwater depth and the area or the thickness of the peat layer that is above the groundwater. So we built a fairly simple model for that, and with that model we updated the old observations. Of course, these are not as good as accurate as real new field observations. There is some uncertainty associated to that, but we took that into account in our prediction framework. So we were able to combine old data with new data. And like I said, we use a geostatistical method for that. That is called kriging with external drift, sometimes also referred to as regression kriging for those of you who know a little bit about geostatistics, in which you combine kriging with information that you get from these environmental variables, like I said, terrain properties, groundwater tables, etc. Can I have the next one, please? So this is fine, thanks. So with the data that we got, we modeled the thickness of the peat layer, we modeled the starting depth of the peat layer, but we also had to model presence absence of peat, because you only want to predict a certain thickness of the peat where you are likely to find peat. So a third say property that we modeled here in the study and mapped was the presence absence of peat, so the peat distribution. We did this say prior to the machine learning era that we now have for digital soil mapping, and we used say a classical statistical model, which was the logistic regression model, which is a model which you can model presence absence data. And then we had a kind of simulation approach in which we combined. So we had we simulated presence absence values for every pixel in the map. We made gridded soil maps. So for every pixel in the soil map, we simulated a presence absence value, so a 0 or a 1, 1 meaning present, 0 meaning absent, a thickness value, and a starting depth value. So the simulations were repeated 1,000 times. So for each pixel in the map, we had 1,000 thickness and 1,000 starting depth values and 1,000 simulations of peat presence or absence. And from that, we could construct soil groups. So we combine presence absence with this thickness value and the starting depth value. So for every pixel, we came up with a kind of a probability distribution of possible soil groups. I can have the next one, please. Here you see the two outputs. So on the left-hand side, you see an example of the thickness map. So we have a class with thickness 0, which means peat is, and this is one part of the peatlands. The peatland in the Netherlands is much bigger, but we did it part by part. So this is one part in the north of the country. So we have parts where the thickness is 0, so their peat is gone. And then we have areas with a thickness value of between 10 and, I don't know exactly what the maximum value were, a couple of meters where we still have peat. Like I said, we combined that with a starting depth map, and then we came with this general soil classes that you see on the right. So some areas are now classified as mineral soils, so peat is completely gone, or we predicted peat gone from there. PT soils, so thin peat soils, and peat soils, which are in our case the thick peat soils. Can I have the next one, please? So from these three main soil classes, these three classes that were in the previous figure, we supplemented that information with some information, say, on more static properties to turn those three major soil classes or peat soil classes into a new classification. And the result you see here, which you see two map fragments. And on the left-hand side, you see the original 1 to 50,000 soil map, and on the right-hand side, you see the updated version. And when you study the classification codes, I'm not going into detail here, but you see that peat got thinner at many locations in this area, in this example area, and you also see that also at some locations, especially in the bottom figures, you see purple areas disappearing and green areas or greenish areas popping up, where you see that peat soils are gone and we have now mineral soils there that were originally under the peat. Next one, please. I think we move on to Finland now. So like I said, this is not about mapping peat distribution, but acid sulfate soils, but methodologically it's exactly the same. So I think that is also why I think it's relevant also in the light of this conference and the work that is being done in the Eat2Soil Agri project. This was a collaboration with the geological surveys in the Nordic countries, in Finland, Sweden, and Norway. We started collaborating with them in June last year until April this year. They did all the mapping and modeling themselves, but what we did as ISRIC, we provided training courses on digital soil mapping. So we did a 1-week course for them in June last year, and we had various technical backstopping sessions between December last year and April this year. So they started working, and then once in a while we met, we had a session and we discussed issues with the modeling, we discussed some methodological challenges and plotted then a way forward. So this was really a nice collaboration. Can I have the next one, please? I will try to speed up a little bit. So here we use machine learning, and as predictors we used also some derivatives from the digital elevation model. They had very nice coverages, especially in Finland, of gamma radiometrics and quaternary geology. So these were good predictors for mapping the distribution of acid sulfate soils. Mapping distributions basically means mapping presence, absence, right? Do we have acid sulfate soil or peat soil, yes or no? Can I have the next one, please? When you do this with a machine learning model, in this case random forest, and we had an implementation in R that we used, you have two choices that you can make. Either you model and predict directly the presence and absence of a soil class. In the case of this project, that will be the presence of absence of peat. Or what you also can do is you can predict the probability of peat or an acid sulfate soil being present. And that is a very nice feature. I can have the next one, please. And I think the latter is preferred. It gives you, because when you predict the probability, it gives you some degree of uncertainty. You predict a probability that peat soil can be found, but there's also a probability, sometimes it's big, sometimes it's small, that there's no peat there. It shows you some of the model uncertainty. And of course, in the end, for an end user, you might want to classify the probabilities into a hard class, presence or absence. And when you have probabilities, you can play around a little bit with the classification threshold. Of course, you can use a 50-50. So when my probability is larger than 50%, I will classify a location as peat. And if it's smaller than 50%, it's not peat. But you can play around with it, and that can be interesting. And I will show you in the next slide. I'm almost done for the hosts. When you model presence absence, it's true, false, yes or no. And when you do that, your result will be a table like this. You have a predicted condition, predicted peat, yes or no, and you have an actual condition at that prediction location. Did we observe peat there, yes or no? From those two, you can make this 2x2 cross table. Like I'm not going into details here. You can look up how it exactly works. But you see that you have some true positive and true negatives. Those are the correct predictions. You predict what you've observed, and you have the false positives and the false negatives. The false negative, you predict absence, in our case, of a peat soil, while in reality we have peat there. And a false positive is the other way around. We predict the presence of a peat soil, but in reality there is no peat there. And by playing around with this classification threshold to convert probabilities into a hard classification, you can control these true and false positives, and that can be attractive. And I will show you in my next and final slide. So this is just something to think about when you. Sorry, next one, please. When you start modeling and mapping peat soils in Latvia with some digital soil mapping machine learning techniques, this is some food for thought. So what I want to highlight here you see the effect. There are some tools like an ROC curve you can use to kind of guide you to selecting a good classification threshold. I'm not going into details here, but what I want to highlight here, that different classification thresholds can give very different results, even though the overall result, when you look at the map, at the accuracy of maps, how well does my model do? How well do I predict the actual observations? We see here 3 examples of models that predict equally well. So all models are almost, the accuracy of these models is almost the same, but you see very different cross-tabulations, very different distributions between predicted presences and absences. In the first graph you see, and then I will finish. You see that so in the columns are the observed, the observations, and in the rows of the table are the predictions. So here you see in the first example, you see that 50 plus 40 at 90%. I have 100 observations here, validation observations. I predict presence of peat, while I only observe peat at 50 of these locations. So in this example, I choose my classification threshold in such a way that I'm really overestimating my peat area. So my map gives an overestimate. The peat area is too large compared to reality. However, my map does capture all the actual peat soils. So if you really want to make sure that you have all the actual peat soils covered in your map, then a classification threshold chosen for this one, it's just a hypothetical example, could be good, but that really depends on the application, on the end user. What does the end user want? Is it important to make sure that we have included all the actual peat soils in our map, even if that comes at the cost of overestimating the area of peat soils? And then in the third example, you see that the other way around, the model is as accurate, perhaps even more accurate, because here I predict the right class at 65% of the location. So my model accuracy is 65%. In the first example, it was only 60%. So you could say that the third model is better, or the third classification threshold. But here you see that, that I mainly predict absence of peat. 75% or 75 of locations I predict peat absence, which includes areas which I do have peat. So different. So the real message is here: different classification thresholds, different accuracy, but maps will look very different. And it's really then up to the use of the maps what is important to decide on a classification, on how you want to classify your probabilities when you want to model presence of absence of, in our case, of peat. Can I have the next one? Next one is just an example of the training that we did, and here you see an acid sulfate salt probability of occurrence map on the coast of the east coast of Finland. That was it. Sorry for talking a little bit longer than planned. Back to you, back to the host.
Thank you very much. We will actually pick up from the place where you ended, and we'll continue from the kind of Latvian perspective now, adding just in between Netherlands and Finland. There is Latvia, the great country, and by the way, the great citizen of it is Mr. Imants Kukuļs. He is Program Director for Environmental Sciences in the University of Latvia. Sorry, I have to... Es gribu jums prasīt tā. Jūs tātad interpretēsiet vēl pa savam šos datus. Mēs redzam, ka nīderlandiešiem būs sava pieeja, somiem būs sava. Nu, tad mums būs, cik mums tagad ir 27 valstis Eiropas Savienībā, vēl kāda cits Eiropas valsts nāks klāt, kur katram būs savādākas šis kartējums, savādāki mērījumi. Nu, tā zinātne vairs nebūs tāda vispār lietojama. Viņa būs ļoti lokāla, interpretējama, un varbūt kāds, kas mācās statistiku, vēl teiks, nav nekas labāks kā sajaukta statistiskā sistēma. Tad nav ko salīdzināt, neko nevar salīdzināt. Katrs darīs tik un tā, kā gribēs. Vai te nerodas tāds zinātnisks kāzus?
Manuprāt, ja mēs tā, ka kūdraukšņu kā izdalīšanas vai konkrēti kritēriji visiem ir vienādi, ko mēs uzskatām par kūdrauksni, tad kā izejot no pieejamiem datiem, pieejamiem resursiem, mēs varam prognozēt šo te vērtību ir vai nav, kurās vietās. Tas varētu būt atšķirīgs, bet šim te kopējam visam rezultātam, ja mums sākotnējais lielums, ko mēs vēlamies ieraudzīt, ir vienāds, tad būs tāpat tās salīdzināmas.
Var cikot, jums kā zinātniekam tas nemulsina. Man kā žurnālisti vienkārši mulsina. Jūs ziniet, ir tas trakais teiciens, ka ir meli, liela meli, un tad ir statistika. Tad šis nebūs tas gadījums. Es dzirdu, es priecājos.
Es nebūšu tas, kas teiktu, ir ļoti liels eksperts tieši šajā te prognozēšanā, modelēšanā. Tādēļ arī šodien es piedalos vairāk ar tādu skatījumu no malas.
Lūdzu, dodiet mums to, jā.
Kā tad vispār, ko tad šī te nozare joma, tas ir šī tālspējas datu izmantošana, un īpaši kūdraukšana, prognozēšanā, kartēšanā tad ir. Principā ir tā, ka tiekot uzrunāts savas intereses un nepieciešamības dēļ, tad veicu literatūras studijas, pētījumu izpēti, un tad mēģinās saprast, kādā tad, kur tad ir šobrīd šī te joma, un tad arī mēģināšu šobrīd ar jums īstenībā izskaidrot to savu redzējumu. Paldies doktoram Kempenam par to, ka viņš īstenībā jau parādīja piemērus, kur tad šie tālspējas dati tiek izmantoti, un es savā ziņā ievadīšu arī nākošo runātājiem un kolēģi. Bet tad kopumā, veicot šo te studijas, mēs par tālspējas datu izmantošanu augsnes organiskā oglekļa, vispār oglekļa prognozēšanā, principā varam skatīties no diviem griezumiem. Viens ir šīs ne kūdrauksnes, kas varbūt mazāk šīs dienas tēmā ir piederīgas. Tad šajā virzienā, ja mēs apskatāmies pēc atslēgas vārdiem atrasto publikāciju skaitas konstanti ir audzis un šobrīd ir ļoti liels pēdējos 20 gadus. Bet šī te otra lieta, ja mēs konkrēti pieskaramies šīs dienas tematam, šī te jau konkrēti kūdraukšņu, purvu prognozēšanai, tad šī te joma savā ziņā ir straujāk attīstās tikai pa kaut kādā pēdējā dekādē. Un arī pieejas savā ziņā ir nedaudz atšķirīgas, arī kas tiek izmantots un kā tiek izmantots šajā procesā. Lūk, tad, ja mēs īsumā pieskaramies šim te kūdraukšņu, oglekļa prognozēšanai minerāla augsnēs, tad tur pārsvarā tiek skatīti dažādi tālspējas dati un redzamās gaismas un tuvās infrasarkanās spektra atstarošanās īpašības, un tur ir jau šobrīd pētījumi tiek veikti lokālos mērogos, mazās teritorijās, lai atlasītu kaut kādus precīzākus parametrus, ir kaut kādi savi ierobežojumi, ja augsnes ir nosakta dažādā veģetācija, augsnes tekstura ir granuliskais sastāvs, šis te akmeņainība, bet šeit rādītāji un rezultāti jau ilgstoši palīdz mums identificēt šīs lielumus. Ar kodraukšņu izplatību tad ir nedaudz savādāk. Tur jau tur arī klāt nāk cita lieta, plašākā mērogā arī citi tālspētes produkti tiek izmantot, piemēram, dažādi virsmas modeļi, zemes lietojuma veidi, dažādu multispektru analīzi. Un tad šobrīd no manas secinājums pēc literatūras analīzes ir tāds, ka ļoti precīzi daudzos pētījumos ir identificētas šīs kūdras un purvu robežas, balstoties uz dažādiem, tā skaitā arī apauguma fenoloģiskiem rādītājiem, bet izaicinājumā vēl joprojām ir šeit kopējā ogļu krājas, varbūt kūdras tilpumasas, kūdras dziļuma noteikšanai. Un savā ziņā es nonācu arī pie viena lieliska pārskata publikācijas, kuras viens no autoriem arī mēs šodien jau dzirdējam, tas ir doktors Kempens, un ko es īstenībā iesaku arī visiem, lai apskatīties un izpētīt, lai saprastu šīs iespējas, šīs tālspētes datu izmantošanas kūdraukšņu prognozēšanā. Un tā viens no tādiem nozīmīgiem secinājumiem principā ir tāds, ka jo vairāk mēs grupējam dažādus šos rādītājus ar pareizajiem statistikas modelēšanas datiem, tad lielāku mēs noteiktību varam iegūt mūsu prognozēm. Bet pēc 2019. gada tad ir vēl pagājuši daži gadi, un šī joma turpina attīstīties, un ir vēl nākušas daudzas citas klāt atziņas, un šī lielāka nozīme, kam ir jāpievērš dažādiem fenoloģiskiem indeksiem, pieņemsim, sugu, biotopu kopienām, ko kombinācijā ar šiem dažādiem telpiskiem datiem var izmantot, lai arī oglekļa krājas šos prognozes veikt. Ir arī veiksmīgi pētījumi, kuros dažādi liderdati, kas ir reliefs slīpums, kopā ar radiometrijas datiem var prognozēt pietiekoši precīzi kūdras dziļumu, dažādas digitālos virsmas modeļus un var izmantot depresiju identificēšanai, kas palīdz varbūt prognozēt kaut kādas potenciālās vietas, kur tad kūdra varētu uzkrāties. Tad jau principā šī pētījuma turpinās un jaunas zināšanas tiek gūtas. Kāda ir situācija Latvijā? Uz doto brīdi, ja mēs skatāmies tādā datu par Latvijas kūdraukšņu izplatību, kas iegūti no tālspētes vai digitālās kartēšanas metodēm, ja tādā varbūt nacionālā, varbūt arī reģionālā, mazāka mēroga apgabalos šobrīd nav, bet ir vairākos virzienos tad tiek strādāts. Tā skaitā arī to, ko iepazīstinās mans kolēģis nākošajā prezentācijā. Bet tad esoši citi pētījumi, kas ir saistīti ar oglekļa prognozē, aprēķiniem dažādās ekosistēmās un augsnēs un purvos. Citi kolēģi šeit rādītāji principā liek skatīties pozitīvi nākotnē, ka ir kaut kādi tiek uzkrāti dati, zināšanas, pieredze, arī dažādu augsnes modeļu pielietošanu un iekļaušanu kaut tai arī nacionālā sega inventarizācijas šajos ziņojumos un dažādi pētījumi par meliorācijas ietekmi uz kūdras slāņu biezumiem. Tad šīs dažādie dati, zināšanas liek principā skatīties pozitīvi nākotnē, kāds līdzīgi prognozes un izplatības kartes kūdru purvu varētu arī būt Latvijā sagaidāmas, jo paralēli tam arī tiek uzkrāti augsnes dati, kas arī varētu tikt izmantot šo modeļu pārbaudē, precizēšanai un tā tālāk. Tas īsumā arī viss par to, par manis teikto. Paldies! Un šobrīd tad jūs arī varat redzēt arī šīs ziņojuma tapšanas laikā izmantotās publikācijas. Šīs tad varat droši izmantot, skatīties un sekot līdzi, kā tad šī joma attīstīsies gan Latvijā, gan arī citās valstīs, tā skaitā Eiropā.
Jā, un tiem, kam liekas, kāpēc mēs radām padomju māju fonā, tāpēc, ka tā ir mūsu zinātņu akadēmija, pirmkārt, un otrkārt, tāpēc, ka viņi ir uzbūvēti uz kūdršpurviem, jo, kā zināms, Rīga, mums ir pat tautas dziesma, visapkārt Smilšu kalni, pat Rīga ūdenī, skaidrs, ka tā bija purvaina vieta, kur atrodas Rīga, attiecīgi fotografējot Rīgas panorāmu, jūs būtībā fotografējat kūdrainus apvidus,
Kūdraini, jā, tad upju ielēs palienes varētu būt tās vietas.
Mēs arī vispār Palienu pļavu reģionā esam Jelgavā, tur johaidī, neviens nevar pat kārtīgi pagrabu uzbūvēt. Bet ir viens čalis, un liels paldies par šī čaļa priekšā stādīšanu, un tas ir jūsu kolēģis Ivo Vinogradovs, kurš ir labākais Latvijas caurumotājs, jo man liekas, ka neviens nav tik dziļi racies Latvijā, turklāt dažādās vietās, turklāt ar zinātnisku jēgu, kā Ivo, jo jūs šobrīd esat, Ivo, tas čalis, kas aizpilda, vai ne, to neesošo datu sistēmu, lēnām piepildat, lai veidojās, un paldies par cītīgi iesaisti arī šajā projektā, un paldies arī par tādu praktisku darbu. Es saprotu, jūsu darba instruments ir ne tikai dators, bet arī, pilnīgi reāli zondi. Ja jūs staigājat pa Latviju ar zondi, kā pirms 200 gadiem latviešu tautas dziesmas Krišāns Barons vārds, tā jūs tagad ziņas par to, kas laucīti mēdurā, kas kurā vietā Latvijā atrodas.
Jā, paldies par ievadu, bet man jāsarūktina, es nestaigāju ar zondi.
Jā?
Jā, Imants staigā ar zondi, Imants staigā ar zondi. Esmu tiešām tas, kurš vienkārši sēž pie datora un neredz dienas gaismu un augsni tikai ļoti reti laboratorijā redz.
Mums ir gan tā augsne un tas pētījums un tas caurums, gan tie dati, kas dod mums lielāku pārskatu, jo tieši tas veido to, man liekas, neziņas mākoņu izkliedēšanu. Un kā tad, cik tālu jūs esat Latvijā? Būtībā es dzirdēju, ka mēs esam tādā neziņas fāzē. Jūs to neziņu, principā ar katru darba dienu arvien vairāk tomēr sastrukturējat kā zināšanās. Ko tā rāda?
Jā, es ceru, ka tas tieši tā arī sanāks, ka ja mēs izveidosim zināšanu datubāzi, bet tā zināšanu datubāze vienmēr būs, nepabeigta un vienmēr pieaugs. Ja? Tas arī ir galvenā atšķirība, kā uz dabas zinātnēm skatāmies mēs, kas ir no datu zinātņu viedokļa. Lūk, jā, es šodien pastāstīšu par to, kā ir iespējams, vai ir iespējams, un kā mēs izvēlējamies sastaistīt tālispēti, mašīnu apmācību un lauku darbus, tātad lielu rezultātu iegūšanu tieši lauka darbos. Es tagad bišķīt apjuku, vai man jāpārslēdzās?
Jūs varat lasīt arī angliski. Ja sagatavojat angliski savu prezentāciju, tad turpiniet angliski. Vienkārši man tā ierasts, ka ar latviešiem es parasti runāju latviski, bet mēs jau tagad 21. gadsimtā dzīvojam.
Yeah, I will switch to English because a lot of the concepts I even actually don't know the translation in Latvian. And yeah, I want to thank the previous talkers, especially the Netherlands and Finnish example was really great, and see the fundamental job they've done. In my presentation, I'd like to emphasize the advantages, challenges, and drawbacks of using remote sensing and machine learning in peat soil mapping, but base that assumptions on our own experience in the project of mapping the peat soils in Latvia, distribution of peat soils in Latvia. So everybody, of course, are very familiar what are the main advantages of using the remote sensing in general in natural sciences, so low cost, rapidity, and high spatial resolution. So that was the main reason why we, of course, chose the remote sensing and machine learning, because the amount of high precision, accurate data from remote sensing came into use just, I don't know, last 10 years maybe, into active use. Also, the computer power came into strength, so we can do the machine learning actually on our desktop machines, sometimes, of course, later using high performance computing. But nevertheless, yeah, you could see in the image that the spectral reflectance of the bare soil is quite easy to trace. Of course, when it's open, So, and the spectral data from Sentinel-2 was the main data we used. The other source was spectral or radar data from Sentinel-1. And we really based a lot on LiDAR scanning material of DEM and derivatives. But first, a little remark, which I want to conclude also in the end, that from our point of view, the main challenge is the way how we represent the so-called the truth, or it's not a positive as it used to be. It's not like we're going and digging and just actually finding the peat soil. We rather prove that there is a greater probability that there will be peat soil than anything else. So it's kind of turning negative, yeah? So you have to keep it in mind. So the workflow we used is quite famous. You get the training data, you get the explanatory variables, and you predict. So as more training data, as more explanatory variables you have, a better chance to succeed. So for the training data, we had a quite similar situation as was explained in previous presentation in the Netherlands. So we had a historical soil data, but we didn't know its accuracy. So we cannot actually do the assumptions how it changed. Yeah. So if ever we would know what's the actual methods used and what's the precision there, so we could then proceed as in the Dutch example. But here we just use it as a training group for first modeling, so it will get the base information for starting the field survey and choosing the points. So the distribution of survey points, so we have at least 10,000 at the moment, the points, but of course we aim at 30,000. And both we not only have a points, but also in certain places the contours, the actual contours, so we could learn also the geometry. If I talk on models, so we have actually not one model or not even 6 models, as I wanted to say, but they said it's like 6 model ensembles. So when you use a machine learning, we don't use a individual model, we use a model ensembles, and then inside those ensembles, we do the majority vote. Yeah? For example, if you use random forest to just so when we get any between when we are predicting probability, so wherever it's composed not of one model but of several models. But these 6 model ensembles, I want to emphasize that comes because of the different types of observations we do, like direct and indirect observation. And inside the direct observation, so the places which are actually spectrally seen from the Sentinel-2. And if it's cropland, so it's a piece of land where there is at least some moment, or it should be some moment in the annual circle, so you could see the open bare land, so it's quite easy, but it comes way much harder with the grasslands or the abandoned lands or the lands partially covered with trees, which are still agricultural lands, which are a study area for us. So for this, we use a lot of indirect observations. So I mean, like it's the forest edges, it's the somewhere like saying simple where the shadow is. So you cannot say. So we have to use a lot of interpolation and use a lot of derivatives from the elevation model, from the relief. Explanatory variables are, you can see, like we used for each model ensemble, we use a different set of variables, sometimes going as up to 60 and 70 variables. So the best fit complex of variables. As you can see in the direct observation, for bare land, the main variables were connected with the wetness, with the spectral wetness, also with vegetation index, so also connected to wetness. And then when we go to the land uses which are more covered with a layer of vegetation, more we use the proxies which are from depth of water, from the slope, from the sinks, so different variables. And for indirect observation, sorry, there's a mistype. This is for indirect observations. Again, like indirect observation, I have to extrapolate, and for the territories which are not directly observable, we have to use it's I think 69 for this, for the grasslands. 69. Of course, their importance are measured, and we not always take all amount, but in general, it looks like that. As a machine learning, first, when we started from the historical data, we tried to use the support vector machine. It was very good for us to do this binary classification, presence, absence of peat soil. But further, by collecting more and more field data, we see that it's very much too early to go on this binary presence absence, which would be a last result, the end result. So we switched to random forest because it allows us to use the models or the combinations of factors you could hardly imagine. So we could really do all the spectrum of probabilities, and it also the random forest showed the greater ability to work with parameters to bootstrap them. And for the final phase, which is for the next year, with the full when we have a full field data, we are looking forward to use the already complementary tool of extreme gradient boosting, which now very actual. And just the drawbacks, yeah. From our, one important thing is that the genetic soil classification, the classification we really use for agronomy, agricultural reasons, is not so easy. It's not so suitable to model. Yeah, it's rather some voluntary divisions between the soil classes, so it's hard to mathematically express them. But anyway, it's still a task to come. So modeling is very good for the tasks we saw in the first presentation on the European Green Deal, to report conditions, to report changes, to monitor. That's perfect. But to actually predict soil class, it's not so. It's quite hard. So-called high-tech skills. Yeah, when we started, we were less experts in that. But first of all, yeah, it's a Google Earth engine. We had to acquire the knowledge because it's the simplest and fastest way was to do the primary exploration. Then the programming we are doing in the R. And now we are switching, already this year is processing on high-performance computing, which is just inevitable when we use such a large amount of data. And still the major drawback, it's like this between data science and natural science, it's communicate between each other. As I said, this negative explanation which we use in cybernetics is it's hardly acceptable sometimes for a positive scientist. Thank you.
Thank you very much. I think it's a very interesting job you are doing now, right? It is not a simple data collecting. It is soil, you know, it's so different. It must be you enjoying it a lot. Yeah, it's getting more and more interesting each and every day. So because we are kind of learning a lot in the process, so and we actually don't know how we're going to finish this, but
like what will be gonna.
But to what percentage you think the machine learning idea, which is now available here, gives a kind of percentage of certainty, possibility to measure really at larger scale, to use this big data phenomena to see something we didn't saw until now. So because you are, you know, touching these data, and sometimes we think that data consists a kind of new gold, that this is a digital age now, that if you have a data, you have all solutions. Do you?
No. I wish. I wish. Sometimes it's also a lot of garbage. So, but the probability we are going to it's close to 90%.
Okay.
Close to 90%. But it's again, it's hard to compare what was the actual probability or precision of actual historical data what we use. So it's an assumption. So we float. It depends. So it's if it's a shadow, abandoned, grown with the bushes, then it's 60%, and if it's open land, then it's 90 or 95. So it really
it
goes.
Changes a lot. Yeah. Well, that's the beauty of science, that you are, you know, the nature is something alive. It is changing. So why not to follow it anyway? Good. Thank you very much, Ivo. Now we have a very precise question to our Finnish friends. So Mr. Timo Räsänen works for this very special Natural Resources Institute of Finland. And actually, if I see the numbers that these organic agriculture soils produces in Finland almost half, or maybe in some cases even more than half of CO2 greenhouse gas emissions, then your research actually means to research what we should not touch at all, or what is the whole aim of this data you're collecting? So will you kind of put big signposting later on? Don't go there. This is the marshland. This is the peatland. Don't go there. It's dangerous. You know, don't touch it. No agriculture is allowed. So what will be this outcome of your research, you think, in 10 years, let's say?
Yes, thank you. That's a good question, but as a project, I guess we are not deciding that kind of question, so it's a little bit out of our scope. But what I understand from Finland is that that will not be the outcome. I think it's more like looking for different options how to use these wetlands or these peatlands, agricultural peatlands, in a more climate-friendly way. What are the options? And there are several projects in Finland related to this question. So I think that will be the direction.
Now, you are working also of big data, and so please show us the beauty of your country when you interpret it in the big data.
Yes, sorry, yeah, okay. Yeah. All right, thank you. And yeah, I'm going to tell you about this ongoing project, and the English name is Advanced Spatial Data on Agricultural Peat Soils in Finland. So it started in the previous year and it continues until the coming next year. And we have 4 organizations working on this. So there is a Natural Resources Institute of Finland, there is a Geological Survey of Finland, National Land Survey of Finland, and the Finnish Food Authority. And it's funded by the Ministry of Agriculture and Forestry, this project. Next slide, please. So basically a little bit about the background in Finland. So we have lots of peatlands in Finland. So approximately 27% of our land area is covered by peatlands. And then about these emissions that was just mentioned here, that it is estimated that 10% of the agricultural area is peatlands, but they contribute 50 to 60% of these greenhouse gas emissions of the agricultural sector. So they play a significant role in the agricultural sector and their greenhouse gas emissions. So basically now we are trying to identify the peatlands and more accurately, and but the current data or the previous data what we have had is not accurate enough. For example, in agricultural side, to identifying field parcels that have peatlands. So on that level, we haven't been able to go before. So this ongoing project, the objective is to produce this kind of spatial data on peatlands for the whole country, so that it can be used for planning and implementation of these climate and environmental measures, especially at agricultural lands. So this is the goal of our project. So next slide, please. So basically, I'm a little bit going through this project and introducing how we are approaching this issue. So the project itself can be divided to 5 parts. So we are first collecting all kinds of spatial data, remote sensing data that could be used in the modeling of these peatlands. And then we are collecting all the existing soil survey data, and these two feed into the modeling. And we are also doing field surveys during the project. So we have actually feedbacks between these different parts of the project. For example, we have 3 modeling rounds and 2 field survey rounds. So they are kind of feeding to each other. Modeling gives uncertainties to field surveys, to where should we target the field surveys, and the field surveys produce new information to modeling. And similarly, we develop new spatial and remote sensing data to modeling when the project progresses. So it consists of this kind of process. And yeah, and from there we analyze then the final results and try to produce final data products on these peat soils. So next, please. Yeah. So a little bit about this modeling. So actually, even we are focusing on agricultural lands, we are modeling all land areas at the same time here. So we are using this kind of 2-step modeling approach. So we first model the occurrence or presence absence of peat soils using random forest modeling. And we have a criteria that these areas should have at least 0.1 meter of peat soil, or the peat layer thickness should be this. And then we have 2 modeling methods we are testing now to model the actual peat layer thickness. So we are using Gaussian process regression and geographically weighted regression. And the modeling resolution at the moment is 50 meters. And let's see if we can improve that. But the underlying data is kind of the limiting factor here that can be go into more higher resolution. And one idea about this data is that we model the thickness of the peat layer, so that later, if there are different kinds of definitions of what consists of a peatland, how much peat you should have there. So this data should allow these different kinds of definitions also in the future. So that's at least our target. Next, please. And a little bit about soil survey data that we are using. I have written here calibration and validation, but it could be also about teaching of the models. So basically, we have quite a lot of soil survey points in our country. We have over 2.2 million soil survey points, and some of them are surface soil samples, some are peat layer thickness measurements up to 8 meters. And these cover all kinds of land uses and soil types. And specifically at agricultural lands, we have over 250,000 soil survey points. And out of those, almost 150,000 points are measurements of peat layer thickness. And these are collected by Geological Survey of Finland, mainly by them, but also by Natural Resources Institute of Finland. Next, please. And then the spatial and remote sensing data that we are using in the modeling to this environmental covariates or explanatory data. We, in this sense, we are lucky that we have quite good geophysical flight data from Finland. So we have a gamma radiation data and electromagnetic data for covering the whole Finland. So this will be the most important data in the prediction of peatlands. But we use also a bunch of different types of data, and we are testing and developing new types of data to be used. For example, we have a digital elevation model in 2-meter resolution in Finland, and we are building different kind of indices out of this, which basically come from the topographical features, so slope and wetness, topographical wetness indices, and so on. And then we are exploring the satellite data options. We use Sentinel-2 optical images, and out of those, like vegetation indices and moisture indices that can be derived those. And we are starting to test also these kind of synthetic aperture radar images from Sentinel-1 also, that they, in my understanding, they could also be used in estimating the soil moisture. So these are ongoing work. And then we of course have existing soil maps that we use, and we have also deglaciation related maps, so those areas that were covered with water and which stage and to what extent, and that also affects the peat depth, for example. Next, please. Yeah, and quickly about results. The project is ongoing, so we don't have too many results to show, but we first saw a little bit something about the soil survey results or existing data and the new data that we have gathered. So what we know out on the base of this data is that on average, the peat layer thickness at field is 1.2 meter, and at 50% of the fields, it's between 0.6 to 1.7 meters. But there are also fields where it's more than 8 meters thick, the peat layer. So this is, we don't know how representative these values are because these are just soil survey samples, but they give a rough direction at least. Then one interesting thing is also in the lower left corner is these organic carbon profiles in peat soils, what we have analyzed. So we have analyzed in this figure 71 profiles. So we can see with the red and the brown color, we can see the mean of these samples. So basically in the surface layer, it is smaller. The organic carbon content is smaller, around 30%, and it approaches 50% in the deeper layers. And the significance of this is that it affects the identification of peat soils. For example, there are thresholds for organic carbon, what is considered peat soil or organic soil. And in some cases, the surface soil goes below these thresholds. So there might be, but this can complicate the identification of peat soils, especially if it's done on the base of surface soil samples. And on the right side, there is just an image to illustrate this soil survey data that we have and in different field parcels. So these are field parcels and how these soil surveys are done. And then we use these kind of locations, for example, validating our models then more precisely, that how well we can identify field parcels with peat. Next, please. And here is the first modeling result about this peatland occurrence or presence. And this is from the random forest modeling. So on the right side, we have the whole country results. And then on the left side, we have a one sample, just few field parcels. And with the blue, we have the model predictions that these areas should have at least 10 centimeters of peat. And then with all the dots are observations, so field survey observations, and the green areas are just simple interpolations from the field observations. So we already see at this point, even we don't have final results, that the modeling results are reasonably good and they are promising for this purpose of identifying field parcels with peat soil. But this will change as the project progresses, but I'm happy about this result. Next, please. Yeah, and the final remarks about our work is that really everything is in progress at the moment. So we are still developing data and we are testing different modeling approaches and ways to model. And the modeling is ongoing. Field surveys are ongoing this year and also still next year. And what we have learned so far that on country scale, this requires quite large computational resources. So the model runs can take some weeks even in high performance computing environment. but the first results are promising, and the actual accuracy and the goodness of the end result we will see at the end of the project. So that will be an interesting thing to wait for. And one thing what we wanted to include also here, we wanted to separate different peatland types, and also we wanted to consider the carbon content, but we were not able to include it in this project, mainly because of data limitations and also resource and time limitations. So thank you. This was the Finnish work, and there is also my email if someone wants to know more about our project. Thank you.
Thank you. One of the things I'm thinking how I'm going to use your email is sending congratulations in the day when you will get into NATO. What a historical year for you, isn't it? And talking about history, actually there is a new kind of division, and exactly this year there is a new standard which is called WERB, which takes into effect just now. So how much does this affect the project? Because the whole project itself was based on this like previous etiquette of the world reference base of 2014. And I understand you still work with these kind of old standards.
Well, that's a tricky thing, because many of these soil samples that we have, soil survey samples, they are visually kind of, we have carbon content measurements also. There are two things. There's the carbon or peat soil thickness and the carbon content. So these are the two things that we are playing with. So we are trying to make it so flexible with these modeling results that if there are changes, for example, in the thickness, peat soil thickness in these definitions, so that can be considered later on also. But we are not able to consider, for example, the carbon content. So that's the part that in any way cannot account. And yeah, basically, I don't know if I can answer better to that, but.
Well, anyway, there is someone who is doing it in a kind of larger scale, and probably with a kind of new aim actually for this, not only agriculture but also environmental. And this is one of the, well, thank you. Sorry, Timo, I didn't tell you. Thank you very much from our side.
Yeah, thank you.
For this nice example. But now the example will come from Emanuele Lugato. He's working for European Commission for Joint Research Center, but actually safeguarding this very special project by European Commission that is actually measuring the whole continent from above, from the sky, from the space, and probably with a little bit different reasons, not only those scientific reasons you share. So it's interesting to see the parallel project and learn what are the impacts and where are these maybe data you could even share in between each and other, isn't it? So welcome, Mr. Lugato. Please explain your observations of your beautiful project.
Thank you a lot. Thank you a lot. And I hope you can hear me well.
Yes, we do.
And you can put my presentation. Okay.
Yes,
thank you a lot.
They are.
But indeed, I'm very glad to have the opportunity to explain, to give an overview of the SEPRA project. Next slide, please. Which indeed is a project in collaboration with DG Clima, which commissioned the project. And the main aim of the project is to help member states in improving the inventory of wetland peatlands, and in a second phase also to monitoring the status of the ecosystem by remote sensing and explicit geographical data set. The project also involved the DG Agri because of the new conditionality on the introduction of the GAEC 2 in the new CAP, which aims to, let's say, protect and preserve these organic rich ecosystems. So one of the points of the project, first of all, is to bring at the same table, different actors and different, let's say, experts. Next slide, please. So the project, SEPRA doesn't want to somewhat create a really new map. So the GRC doesn't want to create a new map, but the main aim is to do the best use of available data and knowledge by member state. And the aim is to somewhat reach let's say, wetland classification according to the IPCC guidelines, in particular focusing on the organic soils and under the agricultural use, cropland and grassland. Next slide, please. Again, one click. Okay. This is very urgent since some study from the, for instance, from the Greifswald-Meyer Center found out that what the member state report under the agriculture organic soils emissions are very likely underestimated. One click, please. And the reason are that in many member states there is sometimes outdated data set. There is a low stratification of the informations, and also a lot of semantic problem. Next slide. The semantic problem are also related to the fact that there is inherently, let's say, variety of the wetland ecosystem. So wet ecosystems are somewhat either permanently or seasonally saturated by waters, but there is also mineral, let's say, wetlands. We are focusing, of course, more on peatlands, on ecosystem that, let's say, accumulate in times, in millennia, an organic deposit. And one of the problems that we found out is that these ecosystems are mapped by different, if you want, expert, different communities, sometimes by geographers, sometimes by ecologists, sometimes by soil scientists. So there is a lot of semantic problem because the same biophysical entity is mapped by different community, and they use different sometimes language, which provide the same information. Next click, please. But there is also another one. There is also another problem, especially related to peatland. One click more. That is that these peat are often degraded, especially in the agricultural land use, under the ground agricultural land use, and so they lose their wet status, and they are strongly degraded. Also, the organic carbon is lost, and until the level they can be no more peat but organic rich soils. Next slide. And this is another, let's say, point of discussion that we have with the different member states we're working with now to understand until, let's say, which criteria still define a peat, an organic soils, or a mineral soils. And this seems, let's say, simple, but indeed is much complicated, and it matters a lot in the project. Next. So for this reason, we set up this project, the CEPLA, which is, let's say, developing in 5 phases. And it's a very participatory approach. At the beginning, we select 4 member states we are working with, which are Denmark, Latvia, Bulgaria, and Ireland. So the idea was to, first of all, in some test area, collect the data and make a metadata review, try to develop a common vocabulary using a meta models, and integrate the data in order to create a workflow and have that to have at the end of the final, let's say, wetland subcategory map. We are also using starting to use the observations preliminary, which help to classify the data and also to workflow. And but it will be used in a second phase to monitoring the peatland management. Next slide, please. Yeah, as I said before, one of the problems we encounter with the member state is that the same biophysical entity is mapped by different communities, so there is a lot of semantic problem, and we created a semantic meta models this model is like let's say is taking a virtual sample of a land cover, considering different strata, as the stratum 0 in this case, the pit deposit, and each stratum is basically divided into classifier in a hierarchical way, which let's say describe the biophysical characteristics of the stratum. Next slide, please. So this approach, it's indeed very simple. Yeah, another one. At the end, it's in a Excel files now, where we put all this hierarchical status of the meta model. So one click more. Whatever land cover, land use that we have can be mapped according to this qualitative or quantitative information, and so we can create a passport of the candidate wetlands or peatlands, which let's say somewhat allow to get rid of the if you want the local or national or field classification, but represent the biophysical, let's say, characteristic of our land cover. Next slide. So the next phase was to also to integrate the data, and the meta model was very useful. I'm not going into detail on this, but I just wanted to say that we use the database, different source of database provided by member states. So wetland, land cover, the soil maps, the LPAS, GSA, all this information. And again, sometimes they bring consistent information. It's just a matter of semantic. Sometimes they disagree because they were done in different, let's say, times, or they have different resolution. So we also try to define some rule to give priority to one or others, and following these schemes, we are able to somewhat next slide, identify the wetlands subcategory according to the, let's say, IPCC, which means let's say cropland, grasslands, organic, wet, or dry, or drain, let's on. And also the other land use not belonging to the agriculture. This is just let's say a prototype of a flow chart. This is not certainly perfect. We can see that probably there are areas that are not classified as a wetland. Next slide. And so we started also to use next slide, please. We started also to use the remote sensing to see if we can retrieve, let's say, useful informations, and we see that, for instance, the Copernicus Sentinel S1, so the radar backscatter or the coherence can really provide some clear features of let's say wet ecosystems, and we see areas that are not identified by the current, let's say, data set provided by member state. The next slide, and also we see that also the optical indices like time series and DVI can be really useful to somewhat discriminate between wetlands that are still somewhat wet and areas that are more drained under agricultural land use. So I come to the conclusion. Next slide, please. So SEPLA, it's a very, let's say, participatory process. As I said, we found out that there is a lot of variety of non-harmonized data within a member state. Each member state has a specific local context. And we found out that sometimes there is lack of integration among expert community within the member state. So with SEPLA, we try to bring different actors, try to make more somewhat interaction to exploit all the potential of member states in terms of data and knowledge. And as I said, as opportunity, we offer in SEPLA a participatory approach. We try to knowledge, to sharing the knowledge, to clarify the concept, to make semantic analysis, and try to somewhat create this method customized by member state that can be applied in a broader scale. And that's all my presentation. Next. if you want.
This,
Okay. Thank you a lot.
And giving us really, but don't go away, because we will have some question and answer session, a very short one. Well, actually, the main question and answer session now goes to you guys. I switched to Latvian, so tātad, cienījamie līdzi skatītāji, mēs par jums visu zinām, jo jūs bijāt kopīgā mākonī ar mums 2 stundas, un, protams, paldies arī par katru jūs ieguldījumu līdzinējās darbībās. Tā kā mēs esam diezgan, ja tā teikt, nu, šauri, labā nozīmē, šauri profesionāli, tad mums ir sagatavot pāris jautājumu šajā Menti.com aptaujā, kurā es ceru jūs gribēsiet iesaistīties un atbildēt. Tas noteikti dos arī ne tikai kopības sajūtu, bet arī tādu dziļāku jēgu pašam Latvijā tikai, kā jūs dzirdat, vēl notiekošajam pētījumam, nu, šim projektam. Un, nu, tādā veidā, kā teikt, aicinām katru, kurš vēl varbūt nav iesaistīts, bet gribētu iesaistīties, arī droši atstāsiet savus galu galā datus, ka vēlaties tajā piedalīties. Menti.com, tātad visi kopā lūdzu ieejam šajā caur savām mobilajām ietaisēm, vai arī var galda datorā, tur nav nekāda atšķirība. Menti.com, un tur mums kopā jāievada šis kods, ko jūs redzat arī ekrānā, 35907352. Jūs varat lietot arī šo QR kodu noskanējot, nu, kādu, kuram ir ierīce. Un tādā veidā jūs ierakstot, nu, nonākot kopīgā mākonī, principā saņemat 7 jautājumus, ko mēs tad ļoti priecāsimies, ja jūs esat ar mieru mums atbildēt. Ja? Tad now we switch back to English. So while we wait these questions to be answered, a general question, whoever wants to involve from you guys, from Bas Kempen, from Timo Ratten or Emanuel Lugato, can I get please at least a kind of, if not a direct answer, well, comment on this matter? Are we at the stage that you are kind of scientists assembling data? Well, nice, but as a journalist, I would ask, well, let's do this science very practical. So it should involve really decisions. Maybe we should, you know, cut the agriculture in some areas where the CO2 capturing is done. So don't touch this soil at all. And that could be a kind of your job, the scientist's job, to suggest in which areas, how should local politicians, municipalities or ministers of agriculture react really on this? Are you ready to give political advices? Should I be like a teacher? So can I ask this question please to Dr. Kempen?
That's a good a good question. I think as a scientific community, we should be able to provide advice, of course, to our decision makers that can help them to guide their decision. But often I think, at least when you look at the situation in the Netherlands, there are, how do you say, multiple interests at stake, right? You have the interest of environmental protection, but also you have the farmers' interest. So there are a lot of interests. They have to balance these. And I think we should be able to give guidance or advice on that from a scientific perspective. But in the end, it's up to the decision makers to make these decisions. And I think the main challenge here, and I think one of the presenters mentioned that, I think there was a presenter from Latvia who did the modeling. I think the main challenge for the scientific community is to how can we present our results in such a way that they are understandable and actionable. I think that is something that we should look at, and perhaps also get a good understanding of what the decision makers want. What will be the use? We can make a map, but of course you make a map for a user. What is the intended use for this map? And that might also guide some of the decisions that you make in your modeling.
Good. Well, let us measure the same kind of question to Mr. Rassen.
Can I complement? Sorry.
Yes, Mr. Rassen.
Yeah.
Please.
So, yeah. If I can complement.
Absolutely. Absolutely. Yes.
Yeah. Yeah. We know. So that in Europe the agriculture is subsidized by the CAP, so it's driven by the CAP, by the Common Agricultural Policy. And indeed, the new CAP is trying to preserve also the peatlands with introduction of the new GAEC. But of course, if we want to rewet, we have also to reward not the farmer, because they have to do an alternative use of a peatlands. And so there is eco schemes and also rural measurements, the measure that member state can implement, and in a way that okay, we ask the farmer, but we also compensate the farmer for the new service that a pit can do, which is, let's say, to increase biodiversity or to release less carbon and something like that. So this has to be viewed under the political context and under the CAP.
European Commission, Emmanuel, I'd like to ask you, what do you think could be a nice timing when to do this kind of outcome and explanation to the wider public, to, let's say, realities of this project and your project and different like data you will have on a table? Because there is this global achievement we want to get is 2030 is the minimum, and the maximum 2050. So the Green Deal thing. So there is less and less minutes actually ticking. So you will do your job, and then there will be a very short period when we will communicate to people. So they will hate it if we don't communicate well in advance with logical explanations, getting them to understand, to accept that reality will change, especially for farmers and forestry industry probably as well. Yeah,
it's right, but the Commission is acting, no? The Commission is acting and is trying to, let's say, to bring the member state into this new, let's say, green dimension. Then there's not only the, let's say, the Commission power, also member state, the Council, the member state has to agree. There is a lot of initiative like the soil mission that are, let's say, putting the soils as a first priority, and the restoration law, the new reform, LULUCF reform, the CAP reform, they are all, let's say, going in the same somewhat direction. To protect, to make more sustainable, let's say, our way we treat the soils in general. So I think there is anyway great effort in moving forward.
Good. And now to Mr. Räsänen, I'd like to kind of switch to a different topic. Could you please name a kind of real benefits, since we can use this new system, digital mapping, the method? So what does it give? A greater, more precise? If you just compare it to traditional surveys, traditional methods we used before. So now the digital age is here. So what do you think is the best thing? That you, in your profession, involve some digitally skilled scientists as well? You kind of do a combination, or there is a greater outcome for me as a simple citizen of my country?
The biggest benefit of our work maybe is this, that because these environmental measures, they are targeted on field parcel scale, basically. So we are getting out of this project a systematic data which hopefully produces or provides accurate enough data on field parcel scale. So that is the main benefit, and so far we haven't had that kind of data that we can target or plan measures accordingly. So, and it's important also that it is systematic and also independent. So this of course provides new big opportunities to looking at agriculture.
Have you tried already to sell, to communicate these data to people who probably dislike it, like farmers or whatever, or maybe the ones who admire this, environmental organizations? So have you already this experience when you start to talk, data language? You're not in favor or against, you're just giving us a full data. What are the emotional reactions of the people?
We are getting feedback from the farmers. For example, we are asking for the permissions for the field survey, and we have reporters have been contacting us, and they have been in the newspaper stories about that. So basically, we try to communicate about our project's goals very well, but there are of course always concerns. So people are of course concerned because there are lots of farmers who depend on their lands, which are peatlands. So there is a genuine concern from their side that what is their future. So that is a real issue, of course, here in Finland.
So you're not the most popular scientist in their eyes, right? They rather want you to leave their estate instead of coming. No?
That's possible sometimes, yes.
Yeah. Well, anyway, we are happy that you are there and your input was very important. I don't know if you managed to answer these questions. They are 7 questions, and more or less all of you so far did answer them. But we asked a very special person, the one from the Latvian side who is supervising this project, Kristiina Sirmā from the Ministry of Environmental Affairs. So to, agriculture, sorry. Oh, Kristiina, oh my God. We are just in this nice green environment of agriculture. Anyway, Kristiina, can I ask you to interpret a little bit and comment on these data? Why you asked these particular questions and how happy you are with the answers, please?
Jā, paldies, Ansis. Tad latviešu valodā turpināšu. Jā, šos jautājumus mēs uzdevām, jo, protams, mūs interesē arī mūsu klausītāju, tie, kas piedalās dalībnieku, tātad redzējums par to, vai šie digitālie risinājumi un kā tie palīdz, vai tie ir super vienīgie risinājumi, vai tomēr tie ir kaut kādi palīgi rīki, jo, kā minēja arī ievadrunā mūsu valsts sekretāra Dats Arāja, tad mēs uzskatām, ka šie ir palīgi rīki, kas ļoti, ļoti palīdz taupīt dažādus resursus, kas ir cilvēku resursu, laiks, un kas, protams, sniedz lielākas iespējas arī ar mašīnu mācīšanu palīdzību domāt jaunus risinājumus, izmantot šos datus. Un skaidrs, ka ar šo projektu kopā, tāpatās arī šodienas runātāji, kas pārstāv citus projektus, mēs redzam, ka ļoti daudz, kur vēl ir mācīties, kur ļoti daudz ir izzināšana teorijā, tāpat metodoloģijā. Mēs dzirdējām Barits kunga uzstāšanās laikā minēja par šiem te ļoti daudziem indikatoriem, kas būs jānosaka, kur dalībvalsts vēl savā starpā diskutē. Tāpat kā šos indikatorus tālāk monitorēt, kā tos verificēt. Ļoti dažādi jautājumi. Un paldies visiem, kas ir snieguši atbildes un varbūt vēl pēdējo minūšu laikā var atbildēt. Tad mēs šo informāciju, protams, vērtēsim. Tā kā tas mums ļoti noderētu. Un jā, šis projekts, kas ir Norvēģu finanšu instrumenta projekts, ilgtspējīga augsnes resursu pārvaldības uzlabošana lauksaimniecībā, ir tiešām projekts, kas ir laikā. Jāatzīst, mēs viņu pieteicām 2016. gadā, un tieši tagad mēs redzam, cik ļoti tas ir aktuāls. Un ar visiem partneriem un arī mūsu šodienas runātājiem mēs esam savādākos veidos, varbūt arī sadarbojamies vai sanāksmēs, vai arī tāpatās kaut kādā veidā datus verificējam savstarpēji, jo mēs redzam, ka mēs nevaram vairs dzīvot un strādāt un pētīt kaut ko tikai nacionāli savā līmenī. Mums jāskatās, kas mums ir reģionālā līmenī kopīgs, kā mēs varam izmantot datus, kā mēs varam apvienot zināšanas. Un augsne tiešām ir atgriezusies globālajā un politiskajā līmenī. Un šis aktuāls jautājums ļoti, jo tātad augsme ir viens no risinājumiem, kā mazināt klimata pārmaiņas, kā piesaistīt oglekli augsnē, kā noturēt oglekli augsnē. Un kā jau minēja arī savās uzstāšanās, mums ir vidējā termiņa risinājumi, kas ir uz 30. gadu, kā arī Ants minēja, šis zaļais kurs, kas ir kurs uz 30. gadu, kā mēs varam sasniegt šos mērķus Latvijā un arī Eiropas Savienībā. Tāpatās mums ir ļoti svarīgi skatīties uz šo klimata neutralitāti, kas ir 50. gads, un augsne ir viens no šiem jautājumiem, kas ir jārisina. Skaidrs ir viens, ka digitālie risinājumi tie palīdz mums, bet ja mums nebūs augsnes zinātnieki, ja mums nebūs eksperti, ja mums nebūs agronomi, ja mums nebūs tiešām speciālistu, tad tās ir tikai tehnoloģijas. Mums ir nepieciešams zināšanas, lai izmantot šīs iespējas, ko tiešām katru dienu mainās un ir jauni risinājumi. Tāpēc rīta 1. septembris, un es noteikti aicinu jaunos studentus, varbūt vēl 12. klases beidzējus tomēr domāt un startēt un mācīties un papildināt zinātnieku pulku, jo mums tiešām tie jautājumi būs ļoti aktuāli. Skaidrs ir viens, ko es varbūt pašā noslēgumā gribu teikt, un man ir tiešām ļoti liels prieks visiem, kas piedalījās. Mūsu runātājiem es lielu paldies teikšu arī tūkiem, tāpat tās arī moderatoram. Ļoti liels paldies un arī sveiciens mūsu norvēģu kolēģiem Nibio, kuri arī mūs ir attālināti klausās, mūsu sadarbības partneriem projektā. Un varbūt noslēgumā, kas man tiešām ir ieķēries strādājot pie šī projekta, un varbūt šodien kontekstā ar šo tēmu, Latvijas Nacionālā attīstības plānā 2021. un 2027. gadam ir ierakstīts: Latvija strādā gudrāk, nevis vairāk. Un, manuprāt, mums šis ir jāizmanto, un es domāju, ka tas attiecās ne tikai uz Latviju, bet arī uz Eiropas Savienību, kā mēs varam izmantot šīs dažādās iespējas, kā apvienot, kā projektus attīstīt un, protams, politikas veidotājiem, kā sadarboties ar pētniekiem. Un pamatā mums klients ir zemnieks, zemes apsaimniekotājs, un visu, ko mēs darām, mums ir ļoti vienkāršā valodā jāizstāsta, un kā tie rezultāti, kas tieši ir tas, ko mēs nodosim jau tālāk lauksaimniekiem izmantošanā. Šodien bija tehniskāka saruna tiešām par metodoloģijām, par tehnikām, un man ir prieks arī, ka mums ir zemnieki klausās. Atgādināšu to, ka projekts turpinās vēl septembrī, oktobrī. Būs liela mēroga daudzos pagastos, notiks vēl zemju apsekošana. Universitātes kolēģis jūs atpazīsiet, droši varat iet klāt un jautāt, ja ir kādi jautājumi, bet liels paldies arī līdz šim tiem lauksaimniekiem, kuri ir iesaistījušies projektos, kuri ir piekrituši, arī jau kur tiek veikti dziļrakumi. Tiešām ļoti nozīmīgs darbs tas ir izdarīts jau līdz šim, un vēl liels darbs ir priekšā.
Pagaidiet, tad mēs arī rokam tikpat dziļi kā Somija, 8 metrus?
Nē, 8 metrus mēs nerokam. Tik dziļi mēs nerokam.
Cik dziļrakums ir Latvijā? Es nemaz nezinu.
Mums ir kopā, man liekas, 15,000 dziļrakumu laikam jāuzstājas.
Tas ir
kopējais, jā, bet
cik dziļi viņi ir Latvijā? Metrs, ok.
Metrs.
Metrs jau ir dziļi. Labi ir. Es vienkārši domāju, es
kādreiz dziļi
ieracies zemē, varbūt bērnībā, bet es nemeklēju kūdru toreiz. Labi, bet ja nopietni, paldies, pirmkārt, ka jūs tiešām tik svarīgas lietas uzrunājat un plānojat. No savas puses, paldies jums, Norvēģi. Kur tā nauda paliek, vai ne? Mēs liekam lietā un pētam patiesībā pasaulīgas problēmas. Jo saprotams, ka mums savā ziņā ir arī jālepojas. Ja? Diezgan liela Latvijas teritorija ir kūdra, un tur paldies Somi, ka mēs no jums varam pārņemt pieredzi. Paldies, starp citu, arī mēs varam pateikt pašiem latviešiem, vai jūs zinājāt, ka viens čalis, kas pirms 100 gadiem aizceļoja no Latvijas uz Īriju, savukārt Īrijā pastāstīja, ko vēl ar kūdru var darīt. Tas nav baigi vidē draudzīgi, bet tāda čaļu mājā kādreiz tika nodibināta Īrijas republika. Vienkārši, lai jūs zinātu, ka latvieši parasti, ja pieķerās lietām, tad top lielas lietas pasaulē. Tā kā visiem jums ir paveiciet, ka mēs latvieši esam šajā projektā. Šodien jums paveicās arī ar šo konferenci, un rīt mums visiem kopā paveiksies, jo mums te Latvijā rītdien dažus kilometrus no šejienes taps jauna universitāte. Protams, Latvijas Lauksaimniecības universitāte mainīs nosaukumu un pieliks tehnoloģijas sev klāt, tieši par ko Kristīna runāja, ka tu to reālo pasauli var izglābt visdrīzāk kombinējot šīs divas zināšanas tehnoloģijas un līdzinējās zināšanas. Tā kā es vēl veiksmi visiem, kuri, es skatos arī tiešām daudz pasniedzēju šeit šodien bija pieslēgušies. Tagad visiem labu apetīti, izklīstam, bet esam gatavi iesaistīties un, kā teikt, jo precīzāk mēs zināsim datus, jo precīzāk un arī labāk priekš mums pašiem mēs varēsim atbilstoši pieņemt lēmumus, kā rīkoties. Tiekamies kādā citā reizē. Uz redzēšanos. Paldies arī tehniskai brigādei, kas te lieliski strādāja, un paldies arī tulkiem, kas, es zinu, diezgan precīzi visu iztulkoja. Uz redzēšanos.
Paldies.